Okay, can you hear me in the back? Okay, good. So I do have some hopefully helpful comments to make about the dipole, and I know some of you are worried about the electron and positron density, and adding a chemical potential does resolve that. But I don't want to derail the discussion today, so maybe I will talk about it at the end. If I don't get a chance, just immediately after coffee break, come here and I can say a few words about that. And just to give you a reference, if you disappear on coffee break, for the dipole issue, what's a nice paper is the Planck. I must have been now one of 5 people to have read this paper. The Planck 2013 results, paper 27, which deals with this, which deals with a really neat thing that Planck measured related to the dipole. And anyway, we can talk about it after. Okay, but that's just a reference. That has some additional information. So what I want to talk about today is continue. So I showed you this picture of the fluctuations in the Kobe map. And everything that we've been talking about so far, we've been dealing with the smooth universe. And that alone isn't going to explain those fluctuations. So to extract the physics in the fluctuations, what we need to consider is the perturbed universe. So maybe I don't know. Okay. Now I can only sketch for you sort of an outline to get to you to understand why the CMB power spectrum has the peaks and troughs that it does. So that's the end point of where I want to get to today. But if I explained everything and derived everything, it would take forever. So what I'm going to say and outline for you is in this book, done pretty well, that I mentioned to you before, called Modern Cosmology by Stodelson. And basically, what I'm outlining is basically all of Chapter 4, Chapter 5, and Chapter 8. So you can see why I can't go through every derivation. But I'm going to try and just give you the sketch and the big picture. But these are the references for basically all the math, that I'm discussing. So in order to so the perturbed universe, what I mean by that is that we're going to talk about perturbations in the matter and energy components, and in the metric. And also how those interact with each other. So to remind you, and I didn't really discuss it in lecture 1, but when we have the smooth homogeneous universe, homogeneous isotropic universe with GR, then if I was going to write the metric in flat space, it would look like this. So I would have a ds squared. Here's my expansion factor, eta. And then I would have minus d eta squared plus dxi dxi. So this would be for the case of a flat universe, the special case, just to keep things simple. These would be my space components. And this eta that I've introduced, which is now different from my baryon to photon ratio. People call this, so just convention that people call it eta. This is called conformal time, and it's defined like this. So that equals conformal time. And the name comes about because when you have this definition, the A can come outside, and then changing the metric by factor of A, I believe, is just a conformal transformation. So that's why that name is coming about. Okay, so that's the flat universe. And now, if I want to perturb my metric, the first thing I would want to do is write the most general perturbation that I could. So, general perturbation I would write it like this. So, got my ds squared, got my A term. Oh, okay. Great. And then here I would have minus 1 plus 2A. So now A is my first perturbation variable. Then I've got minus 2BI d eta xi. So here's 3 more perturbation variables. Plus 1 plus 2d dij plus 2eij. And then here I'm going to have dxi dxj. Right. And again, this is a flat case just to keep things, just to keep the math simple. So A is a perturbation variable, my 3 B's, I have a D, and then I've got a bunch of these guys. Okay? Okay. Now, if you look in the Dodelson Modern Cosmology book, then when he does this, he's just considering density perturbations. So if we consider only density perturbations, so what I mean by that is that, for example, we're not considering tensor perturbations, like primordial gravity waves would give us tensor perturbations. So that would be in this component here. And this component is largely from vector perturbations. And we actually don't have primordial vector perturbations in the universe. So if we don't consider those, to keep things simple, we consider only density perturbations. And another word for this, we call them scalar perturbations. Then we get this simplification. Keep it like that. So we get ds squared equals a squared eta minus 1 plus 2. And now it's convention to call this A, this, I always forget my Greek, psi, right? This is psi or phi? Psi. I always forget. Okay, psi. And then the other one, I've got a phi here. Xj. Say that again? The question is not in what era. You'll find that when you do all the equations out, you will find that you will have a set of equations that apply for density perturbations and a separate set of equations for tensor perturbations. And you can think of them separately. Sorry. So I'm not saying there's an era in which I don't have tensor perturbations. I'm saying that the equations for the tensor perturbations can be separate from the density perturbation equation.
But that is true only to linear or linear.
We are only doing linear perturbation theory. So thank you for saying that. So let me box that in. What we're doing is linear perturbation theory. Great. That's the next thing I was going to say. We're going to say it later. We can show mathematically that any vector perturbation that would have arisen would decay away very fast. That just comes out from the math. And linear perturbation theory means that we throw away, all higher order terms. So anything that looks like delta rho, and then delta, some component of the metric or, whatever, or, some delta rho, whatever. We throw out all higher order terms. Okay?
So this will not capture any anisotropy of the homogeneity. Is that right? Isn't it still isotropic?
No, this explains our perturbations in our CMB. This explains the CMB and isotropies. They are functions of our coordinates. Hold on, I think I understand your confusion. 1 second. Through a higher order, well, maybe. But that's because these perturbation variables are functions of position and time. And I didn't say that, right? Okay, so, right. So, okay. And we're doing linear perturbation theory. And also, so let me keep this board here. Let me write it over here. So let me write this down. So, well, for this case, psi and phi depend on x and t. Okay? Okay. All right. Now, so that's our metric, perturbations in our metric. And now we need to do perturbations in the matter energy component. So first, let's just remind ourselves what they look like in the smooth universe. So matter, energy, so when we had a smooth universe, and hopefully this fills in any gaps from lecture 1, from the previous lectures if you still had them, for photons, we would describe the energy density as this. So we would have D3P where I'm setting H to 1, H bar to 1. And then I would have E P over T minus 1 P. Okay? Multiplied by P. I'm going to put P here. P. So, why does this make sense? So P equals E here because I've got C equals 1. And this is a density, so I'm dividing out dx cubed. Okay? So my smallest phase space region is 2 pi h cubed. So no particle can be localized in a region of phase space smaller than that. And then, if I want to know how many phase space elements I have, then that's that. Okay, so that's this term, how many phase space elements I have, but then I divide out the dx cubed because I'm talking about a density. Okay? And h is 1. So that's in the smooth universe. And neutrinos are the same thing. So in this case, let me just write for neutrinos, I can define F, which is my phase space density, as just this factor, E, P, but now this is temperature of the neutrinos plus 1. Okay? So here, when I said temperature, I meant temperature of the photons. And now this piece here, this 1 over this, is what I'm calling my phase space density. And it's this for neutrinos. Remember, the P is just coming because I want, this is actually energy density. I'm again making my C's equal 1. So this I mean energy density. Okay. So by 0, I mean the smooth universe. Right, smooth universe. So that's sort of the convention. Okay, so that's photons and neutrinos. And then for dark matter and baryons, it's simple. So I would just have my rho c as a function of eta, which is just a function of time. And then my baryons would just look like rho 0 b, function of eta. Okay. Now I want to perturb things. So let me write on this side over here. So now let's perturb universe. Okay. So for photons, the variable that we're going to perturb is actually the temperature, T. Okay? So let me just stick to writing F, because everything else in the integral is the same. I'm going to have F that's a function of position, the momentum, and eta. And that's going to equal, I'm going to have my exponential, and in here, instead of that, now I'm going to have eta minus 1. Inverse. So instead of P divided by T gamma, right, this is P, I can put a T gamma here, so that's T gamma, but now I have this extra thing, this is my perturbation variable, which we call this theta thing. That, I don't know, wouldn't have been my variable of choice, but that's the variable we use. Okay. So this becomes a convenient way to describe things because the observers actually are making maps of this theta. Right? So theta. It's the fluctuations about the mean. Yeah.
Is it always that that's going to come into play? Like how the perturbations are coming into play? Like there's a very particular choice here for how theta looks, like, or how you put theta. I guess the point is just saying the temperature change.
No, I'm not sure if I understand your question. So I can, what exactly is your question?
This is F of the photons for perturbations.
Mm-hmm.
And you chose to put theta exactly that way.
Yes.
So I guess what I'm asking is obviously you won't have any other effects in your basic distribution. I don't know. You just put it in there.
I mean, I could have maybe, so I made a choice here, a choice that will turn out to be the most convenient. Maybe I could have perturbed the momentum or like something else, but this has become a convenient choice, and so that's why I did it. This way.
Okay, because it's only temperature that's changing.
Right.
Also, you understand the statistical, right? I mean, this is the only input that comes from the state of.
And the photons always follow the regular distributions no matter what happens. Okay, no, that's fine. No, then I agree.
Good. Okay. Now for dark matter, okay, let me just say, so this is photons. I can do exactly the same thing for neutrinos. So the only thing that changes, let me just write it out. So let me put this like this. So I have F x p eta, and then I'll have my exponential p. I have temperature of neutrinos as a function of eta. And now I can just define my neutrino perturbation as a perturbation of the neutrino temperature. Plus 1 minus 1 here. Okay, so just same thing. And if we could detect the cosmic neutrino background, I could make maps of n, just the same way I make maps of the photons. Okay? Yeah. Do I mean to have a P here? We're good? Okay, good. Great. Yes.
So are we assuming for some way local normal equilibrium, and then this function value also to locally, because this is true for equilibrium of thermodynamics. And if you don't have that, then you
So in the early universe, we are in thermal equilibrium, right?
But then this function changes local point. So you're not having overly value some of the switching functions. Fluctuations.
We have, right. So what's... So our photon bearing fluid is going to act like a fluid. So you should think of things in fluid dynamics, like in terms of fluids. So as a fluid that's undergoing oscillations can be in some equilibrium state. That's what we're talking about. Okay? So, our fluid dynamics, is going to hold here. Okay. So our dark matter is going to look now like rho c and we're going to have the smooth rho as a function of time, and now we're just going to have this 1 plus delta function. This is our perturbation, our dark matter perturbation as a function of eta. And we have this, which is our dark matter perturbation, and also we're going to have a velocity, a dark matter velocity as a function of x and t. So matter perturbation and now velocity. We don't have the smooth universe velocity is 0, right? So this velocity is a first order perturbation. Okay. For baryons, no, separate. This is the equation for the matter density, and I'm saying, and also we have perturbation for the velocity. of the cold dark matter. So C means cold dark matter. Okay. And the same thing for baryons. So we're going to have a rho B, X, and our baryon perturbation. 1 plus D baryon, X, and we also have velocity. Okay. Well, it looks, if I had to write the same equation, it would look like that. Right? Because I don't have this piece. Is that not helpful?
I can ask you later.
Okay. Right. Not as a function of position. Right. So, if all the cold dark matter and the entire universe was moving at 100 kilometers per second, I don't know how we would observe that. Okay? So what I'm saying is this is equivalent to this thing, and if I were to write the same equation, I would just not have this term. This would just be 1, and it would just be like a tautology, right? I wouldn't do it. I'm just telling you I also have this perturbation. Okay, now, here I'm going to sketch for you the illustration that's in the beginning of Dodelson chapter 4, because I just think it's illustrative of what's going on. And maybe it gives you a sense of why I can't derive everything for you right now. So I have these perturbations, but they're all interacting with each other. So say in the center, I've got my metric, right? Then I've got my photons over here. And the photons are interacting with the metric. Then I've got my electrons over here, right? So as my electrons change, they're changing the metric, and there's a back reaction, right? Then my photons and my electrons are interacting with each other with Compton scattering. Then I've got my protons over here, also doing the same thing. Everything's interacting with the metric. These guys are interacting with the electrons with Coulomb scattering. Then I've got my dark matter. That, thank God, only interacts with the metric, we think, except you people are trying to make things more complicated, some of you. And then I have my neutrinos. That's interacting with the metric. Right. So all of these interactions are described by these coupled. We call them Boltzmann-Einstein equations. Okay? Yes.
Why don't the protons and the photons?
Why don't the proton? I think probably, I'm guessing the scattering cross sections are too small. Right? This is the main scattering interaction. That's why. Not important. So Boltzmann equations are going to tell us the density of all of the components, but you're going to need collisional Boltzmann equations to take into account the scatterings. And then that's all chapter 4, and then chapter 5 brings in the GR equations, Einstein equations, and so you're going to relate the matter components to the metric, and you're going to get a whole bunch of equations. And at least, you know, in linear perturbation theory, as I said, you can at least throw out higher order terms. Which helps you. So, okay, so let me say a few more things. So, where do you do all of this? Do you do this in real space using variables of x everywhere? No, because it's a big mess. So, what makes things much easier is to transform everything into Fourier components. Okay, so So, if you're not familiar, what I mean is, say I have a perturbation. So all my perturbations I'm going to transform to Fourier space variables. So say I have a perturbation in dark matter. Then instead I'm going to talk about delta as a function of k. Where here's my, so I is my three space components. I indicates my three space components. And I'm going to have E minus I, Ki, Xi, D3, Xi. Okay? Now, it's convention when we talk about Fourier space variables to have no tilde on top. So sometimes you'll see Fourier transform, you'll see a little tilde there, but we tend not to do that. And instead you look for what's in the argument. So you look for a k or an x to tell you what you're talking about. And the reason why we do this, and the big advantage, which I'll just say, is that when you have a homogeneous background, each Fourier mode is actually going to evolve independently. So this gives you a big simplification of things. So if you have a homogeneous background, each Fourier mode evolves independently. Oh, sometimes you just see this. Like if you have a Fourier variable, I just mean nothing sophisticated. I just mean sometimes you write it like this, and sort of the convention, certainly the convention in that textbook, is that we don't. And we just, so you just look, if you see K, you know we're talking about Fourier space. Each Fourier mode evolves independently. So that's often why you see a CMB power spectrum as a function of L modes, because it's much easier to extract the physics from the power spectrum. There are a few subtle things that couple Fourier modes at late times, which I hope to get to in the next lecture. Like, for example, gravitational lensing. So the CMB is the backlight, and it gets gravitationally lensed by all the dark matter between the last scattering surface and us. That can couple L modes together. It's a very subtle effect. But to give you a sense of how subtle it was, my collaboration had the first detection of that at 4 sigma about like 3 years ago, basically. Now Planck has a 40 sigma detection of the effect, but it's just a recent thing of lensing of the CMB. It's a weak gravitational lensing effect, but you have so much structure. Okay, but we'll talk about it more next time. It's actually one of the main things I work on now, and one of the main frontiers of CMB research is mining that lensing signal. Yeah.
So that is even true for last scattering when you have, say,
okay, if you're going to ask me about whether that holds if you have isocurvature, certainly for adiabatic perturbations, yes. We have no evidence for isocurvature perturbation, so I haven't spent a lot of time thinking about it. I think it still holds, actually. I can double check. Okay. Let me say one more thing about these thetas. So I'm going to say one more thing, and then I'm basically going to write down for you the final answers of what are the equations that you get at the end when you do a lot of math. So okay. So first, one thing to note is that unlike the dark matter and baryon perturbations, photon and neutrino perturbations don't just depend on X and eta. So dark matter and baryons, they depend on X and eta. And for photons and neutrinos, we also have to care about the direction of propagation of the photon. So in Fourier space, we say that it depends on, we have K now instead of X, eta, and then we define this convention to define this mu parameter, where mu equals the direction of propagation times our K vector. Okay? So this is just a convention. And so now I would have perturbations defined as K, eta, and mu, in terms of K, eta, and mu. And one thing that makes things easier to do is I can now decompose this in terms of multiple moments, this theta. So the way that happens is I say theta at some L is given by K eta, and I'm going to integrate out this mu. So I'm going to have 1 over, this is the definition, minus I to the L. And then I'm going to go from minus 1 to 1. Let me put this a little higher. Photons are propagating in a particular direction. Right? Right. So photons have direction. So this is a 1 here. 2. And this is our Lujandra polynomial. Okay, eta. Okay? So this is the Lujandra polynomial. Okay. So my theta at a given L, I would write like that. Okay. Great. Now, and let me just say, if I had theta 0, that would be analogous to a density fluctuation. And if I had a theta 1, that would be analogous to a velocity fluctuation. So I'm basically saying dark matter and baryons only have this type of perturbation, whereas photons have a much richer spectrum. Okay. Say your question again. The contribution from what is this spectrum? So certainly if these guys were moving, well, say that again, please. Right. That's right. 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 So when you think of the dark matter, if a dark matter particle is at, at some point in the universe is here, it's basically going to stay there as time goes on. It's not moving anywhere, whereas the photons are moving. Right.
So this is going to evolve with dark matter is already going to be.
We assume throughout dark matter, I know you may have some theories, but we are assuming cold dark matter where it's non-relativistic throughout, and basically a dark matter particle where it's born, it's still there, basically. Okay? Yeah.
This is the epoch of decoupling, right?
No, this applies before that, before the epoch of decoupling as well. But what we're just going to get to is that prior to decoupling, what you're going to find is that the only things that are relevant for our equations are actually these two components for the photons. And I'm just going to get to that in a minute. So let me just get to that. So, all right. Let me keep an eye on the time. Okay. So now, if you go through chapter 4 and 5 in that book, then let me write for you. And let me see how many equations I want to write down. First, let me write the relevant ones. All right, so you're going to get a whole bunch of equations. If you limit yourself to just the scalar coupled Boltzmann equations,
So, talked about theta and then you talked about density and velocity derivatives for dark matter. So, I
I'm just saying, right.
They do not have a mu because they don't have
No. I'm just saying that if you want to understand what a theta zero component would be like, it would be analogous to talking about the density perturbations of your photons. And this would be analogous to talking about a velocity perturbation of your photon. I'm just saying it's just now they're not related to each other. Okay?
They're not related to dark matter at all.
These are not related to dark matter. I'm just sort of saying it's like if you wanted to, have a handle on how to think about it, I'm just saying that you can think of it as this would be like a density perturbation of your photons, and that would be a velocity perturbation. Okay. So okay. So as I said, there are separate equations for vector perturbations and then separate set of equations for tensor perturbations. They separate out nicely. But for these, what you'll have is I'll have a few equations. I have equations that tell me, and a dot means, when I mean dot, I mean d eta. So actually, I think it's a partial derivative. So I mean d eta. Okay? So I'm going to have some equations for how these different moments change as a function of time. And here I'm writing L. So I'm going to... So for the first ones, there's specific formulas, and then there's a general one for all the L's greater than 3. So here I'm going to have minus k theta 1 minus phi dot. And here my k is in the direction of propagation of my photon. So like you pick a direction, you say your photons are all in the k3 direction. And so that's why I'm dropping my k vector. So you pick a direction for your photons to propagate. And then I'm going to have a parameter that I haven't defined yet. So I'll define it in a second. Here is my baryon velocity perturbation. And then here is my potential perturbation. So the equations that we're going to need are going to be these two equations. This is an I. Yeah. And I'll write down for you the next two equations. Actually, we'll need this one as well. And then this one, which we'll need, write it a little lower.
There's no substitute on the first theta there?
There's no, this is a 1. And then this guy is going to be L, K, and then it's going to be related, so L, 2L plus 1, to the previous one, L minus 1, minus L plus 1, 2L plus 1, theta L plus 2, L plus 1, sorry, plus theta dot phi L. And this is for all L greater than 3. Okay? So this is telling us how the photon perturbations evolve. I have basically analogous equations for the neutrino perturbations. And then if I'm going to, let's see.
Sorry, what is tau again?
I haven't defined it yet. Just give me a second. Okay, I will define it in a second. Tau is an optical depth, and it's going to quantify basically scattering. So it's going to tell us how opaque our medium is to photons. So let me write down the baryon. Okay, let me write down the baryon equations because we need them next. So here my potential comes in again. So 3 phi dot minus IKVB. And then I've got VB dot, which is going to be given by minus AH. Remember, H is just A dot over A. VB minus IK phi plus tau R, which I'll define in a second, VB plus 3I phi 1. Okay, so in the interest of time, I'm not going to write the dark matter equations, and there's some additional equations that tell us how the metric components evolve. So I won't write that right now. Here, R is 3 rho baryon in the smooth universe over 4 rho photon in the smooth universe. And that's going to come in, that's going to affect the sound speed of our fluid, this R. And tau is defined as d eta prime, and the density of electrons, our cross-section again, our scattering cross-section A. Okay? So this is basically quantifying how thick our medium is, you know, or how easy it is the photon can penetrate through. And prior to recombination, tau is very, very big. Or prior to photon decoupling, let's write this. Tau is very, very big. Okay? Okay. So, so now let's look a little bit at what's going on. Okay, well let's look a little bit at what's going on prior to recombination now. Because if we want to understand the CMB spectrum, well, we need to understand what's happening just prior to decoupling. Every time I say recombination, I mean decoupling. Okay. So let's look at that L greater than 3 equation. So we've got theta L dot equals K L plus 2L plus 1, theta L minus 1, and then we said we had this, 2L plus 1, okay, and then we have this term. Now, I said, I'm looking at the case where theta is very, very large. Now, I can say that this is approximately, I'm just trying to sketch something for you so to make an argument, to make you believe a particular argument. So let me sketch this out. So this is roughly theta L over eta. This is roughly theta L over eta. This piece, let's ignore this piece for now, and then I'll finish my argument, and then we come back and see why we ignore this piece. And so what we're going to get then is, since theta is very big, what's going to dominate is this piece over here. I'm going to say that that's roughly equal to K over 2. So let's just call this 1 over 2 over here. K over 2 theta L minus 1. Okay, because this term is dominating over the other term there. So then I could say that theta L is about k eta 2 pi theta L minus 1. And now I said that tau is very, very big. So that means that every theta L is going to be much, much smaller than the one before it. L minus 1. Okay? So now it makes sense why I say let me ignore the L plus 1, because I'm telling you it's going to be much, much smaller than the L term. Okay? And what this... Huh? Yeah. We can do that. You can work things out very carefully and solve all the theta L's properly, and you will find that relation. So for purposes of this very short lecture, this is what we do. Okay, thus, in the tightly coupled limit, which is what we're in, prior to photon decoupling, only are theta 0 and theta 1. And you'll find that the theta 2 and above actually are not important. Okay? And so our photons are going to behave like a fluid. Described by some density and velocity. Okay? All right, and then the relevant equations we're going to need to solve things are going to be like the theta 0 dot, the theta 1 dot. We're not going to need the theta 2 dot, etc. But we do need the baryon, these two equations. So when we take those two equations that I starred and these two equations as well, and I put them together, then I get, after a bunch of math, this. I get what's basically an oscillation equation. So you put those four equations together that I starred, and after some math, you get something that looks like this. So I have a theta double dot, theta 0 double dot, plus a dot over a. Here's my r, that same r that I defined before, plus k squared cs squared theta 0, and that's going to equal minus k squared over 3 minus a dot over a r 1 plus r. Here's my dark matter potential. And let's write this last thing. This last thing is some sort of forcing function. So you can see this piece here. Here is my oscillator, right? And here this piece looks like a forcing function, right? Yeah. Yes. Great. Thank you. Okay. And the sound speed of my fluid is going to be 1 plus r, which equals sound speed. as I add more baryons, I lower the sound speed of my fluid. If I had no baryons, it would just be 1 over root 3. So now to give you a sketch of what's going on at this time, so this is just prior to photon decoupling, is that, and I have to make a little bit of maybe I have to sketch things out a little bit for you. But if you think of Fourier modes, and you think that I have some dark matter potential, right? So here's my dark matter potential on a certain scale. Okay, so how do you think of dark matter on different scales? I mean, that's easy enough. Like, you can imagine perturbations on scales of clusters or smaller scale things. Okay, so here's my dark matter perturbation on a large scale. And then I've got this photon baryon fluid, and it wants to fall into my perturbation wells, right? So here's my photon baryon fluid. But when it falls in, because of the photon pressure, that's going to push it out, okay? So, you know, everybody wants to pile into my well on a particular scale, and then the photon pressure is going to push it out again. And I'm going to get some oscillation going, okay? Now, when we see a picture like this, okay, what's going on? Well, we can imagine photon decoupling basically happening at an instant, and we're just freezing the snapshot of what was happening at that instant, okay? So the largest scale that would have had, that the fluid would have oscillated in is called our sound horizon, okay? We have a fluid, and that's telling me, you know, the essentially like the causally connected region of my fluid is my sound horizon, okay? And that's going to be determined by my sound speed. So the largest perturbation I'm going to have is on the size of my sound horizon. And on that size, what was happening is, so imagine this perturbation. So let's say this is perturbation is on the size of my sound horizon. And what was happening right at the instant of photon decoupling, these photons and baryons were falling in and at their maximum compression on this scale, okay? And so everybody was in their wells, and they were on maximum compression. At any scale that's an integer multiple, like right, so any scale that's like say 2 periods can fit into this, so any sort of integer multiples in terms of periods, those photons are also on maximum compression, right? Anything that's an integer multiple. Anything that's exactly out of phase, so the scale, so half this scale would be exactly out of phase, those photons were having their maximum rarefaction, right? Exactly maximally out of the wells, okay? So I got one guy nodding here. Am I lost everybody, or you're like, oh, okay. Okay. No, hold on. Let me get to the end of my story here. So the first peak, okay. So let's not worry about let's not worry too much about the axes yet. The first peak is telling me the scale of my sound horizon, okay? And all the photons were piling in here, and I had an overdensity compared to the mean photon distribution, right? At this scale, they all were piling in here. At a scale that's half that, half that size, that's having its maximum rarefaction, I would have actually an underdensity compared to the mean, Okay? All the photons and electrons were maximally out of that potential just because the phase of their oscillation happened to be, right? That's actually the second peak. So this is the maximum compression. This is the maximum rarefaction. And the reason why is because I've squared everything, because I've taken a power spectrum, right? So overdensities are squared, but underdensities are squared as well. Right? So I've squared everything, so that's why everything's positive. Okay? And then this again is going to be at maximum compression. And actually, all those ripples are integer multiples at the time of photon decoupling of each other. Okay? So odd peaks are telling you maximum compression, and even peaks are maximum rarefaction. Okay? All right. So this is why we call this acoustic oscillations, right? To, pay tribute to the sound waves. And we have them due to the pressure of the photons. And we have actually a never-ending series of peaks and troughs due to this process. Okay. But why today do we see peaks at all these different L's when I just told you that we only have a theta 0 and a theta L, right? So what happens is that the photons are free streaming to us. And if we have, so the reason why we only see a theta 0 and a theta L at the time of photon decoupling is basically because our horizon is very small. So there's a plot in Dodelson, which I always thought was very confusing, but I guess it's the best way to show it. So if you imagine that you have this plane wave, right? And so you might have, overdensities, underdensities, overdensities, underdensities, etc. But if I'm here and my horizon is really small, I'm not going to see all those fluctuations. I'm basically only going to see like a monopole and a dipole when my horizon is small. But later, like today, my horizon is very big, and those photons have free streamed to me. So scales, so if I have fluctuations on scales K, in angular space, they're roughly going to project onto scales K times, and now I'm being a little bit loose. This is my horizon. And I'm being a little loose with my conformal time versus horizon. But what I'm saying is my horizon here. So when your horizon's really tiny, you're only going to see small L modes. But when the photons free stream after decoupling, and I'm not sure if I should, in the interest of time, write out the whole equation, but let me just say that there is a function to take me from, okay, let me take off the eta here. This is my horizon today. Right? Well, okay. And this is going to be some function of theta 0 at the time of decoupling and theta 1 at the time of decoupling, and also my phi K eta decoupling. Okay. And And this long equation that I probably shouldn't write out for you, but it's in the textbook, that analytic equation is the basis for codes that you may have heard of, like CAM or CMB fast. So you've heard of these types of things, right? So that equation, this function, when you can find it in Dodelson, it's an analytic expression that gives you about 10% accuracy over a straight numerical integration of everything. And that allows these codes to do things very fast, to switch the parameters and tell you what the theta L's are. Okay?
Is this function actually fundamentally project out the stuff that you just described analytically?
Say that again?
So this function is what it actually projects according to the type of horizon.
Right. Yes. So this is telling you when my horizon is bigger, now what's the spectrum of L's I see. So it's the free streaming equation. It just tells you how things look when the photons free stream to us. What things look like. And CAM and CMB fast are just taking these coupled Boltzmann-Einstein equations and solving them and maybe making some very small approximations to get complete analytical forms of things and then giving you something that's like 10% accurate. Okay? Born approximation for which in particular? Like there's one for lensing. Oh, for lensing? Are you talking about? For the TT? Okay, let's talk about it a little bit because there's a Born approximation also for lensing. That's a little, probably a different thing. Okay, great. Now, you might ask yourself, great, but you didn't explain why, if I draw my power spectrum like this, why are the peaks falling off? Why is there this fall off, right? Why are they not all at the same amplitude? Does anybody know why? Yeah, we're ready. Okay, and who, given that she said selective, who know, what is it? Well, okay, but what particularly, and when? When, like, you mean free streaming after decoupling? Or, okay, so what's happening? Yeah, like what, so what do you mean? So, right, so what you're talking about is the mean free path of the photons, right? Right, okay. So photons are going to have some mean free path, and so what it means is I drew this nice picture, but the photons are not going to just sit in the little potential well, especially if the potential well is very small. They're just going to free stream out and not stay nicely localized. Let's look at the time. Okay, so just two last sentences about this. So basically, this is due to, fall off is due to the diffusion damping. And that has to do with the mean free path of the photons. And so that will be given by H. So it's basically the distance that the photon travels is the mean free path times the total number of steps it can take. Okay? So we have a fall off in the spectrum, and so our theta 1 and our theta 0 and our theta 1 is going to be multiplied by some exponential term, k squared, kd squared. Okay, so you understand what I'm saying, right? Like my photon is not going to stay localized because it has some mean free path before it scatters again. So while it's tightly coupled to the electrons, it's not exactly fixed to it. So it's going to have some diffusion. And on smaller and smaller scales, that's going to damp out the amplitude of my perturbation just because my photons will diffuse away. Okay? Okay, so now let me, while this is warming up, hopefully, so I'll show you the power spectrum, and I'll tell you what we mean by CLs, because that's what you always see when you see the power spectrum. So we said that our temperature, eta, is given by this 1 minus theta, 1 plus theta thing. But the thing is that what is x and eta for us? We observe at our position, x naught, and at our time, eta naught. Okay? So the only thing that matters for us is the direction that the photons are coming. So instead of these variables, we can use theta and phi, right? Because all we care about is the direction that the photons are coming in. And I can rewrite theta in terms of these spherical harmonics. One to infinity, m going from minus L to L. And then I have these things called ALMs and a YLM. P. Okay? And you can see that I can rewrite ALM in terms of my theta. Okay? And what CL is, let me put this up and this down. CL is just the variance of my ALM. So if I average my ALMs together, then I would get 0. But if I did ALM star A prime L prime, then I would get CL. Okay, so it's basically my ALMs squared and then take the average. So it's just the variance of my ALMs. And then in order to get this quantity, to get this, I'm going to need this quantity, theta k p theta k prime p prime, because that's going to come out in my equation when I try and calculate this. And what's done by convention is to write this theta in terms of a dark matter fluctuation, theta divided by delta. And the reason why is because here I divide out the initial amplitude of the fluctuation, which I may not know, set by inflation or whatever. So this doesn't depend on the initial amplitude, but this doesn't depend on P. So the way we write CL then is CL equals 2 pi 0 dk k squared P of k theta L k dk, where P of k equals the dark matter fluctuation on a scale k. That's the matter power spectrum. So we call this matter power spectrum. And this is called CMB spectrum. So you can see our CMB spectrum is actually intimately connected to the dark matter power spectrum. Okay, yes.
Why is not CA?
Because there's one line I skipped. For each L, for a given L, each LM has the same variance. So let me just write it here. For a given L, each ALM has same variance. Okay, so thems don't become important anymore. Okay, so let's see, what I have here is this one. Input 3. So I'm trying to impress upon you how great our data is. So I showed you, this is a Kobe picture from 1994. Oh, the light. Is that? Okay. So here's our picture from 1994. Here's what happened 10 years later. So you can see that's the WMAP satellite that gave data in 2003. That's when I was a grad student and I started in string theory, and then this result came out and I said, forget it, I'm doing cosmology. I was actually taking a breath course. Cosmology was my breath course. So anyway, you can see those cold spots and the hot spots are there, but just much more detail. And this is the image we have now from Planck. So you can see how everything has gotten much sharper. And our power spectrum, this is the latest CMB power spectrum from Planck. And you can see how tiny the error bars. These are error bars here. These are not just data points, right? So you can see, I mean, you know, I'm sure there are people who talk about the old days with the balloon experiments, but even for me, 2003 we had the first peak and a little of the second. Then the big deal when I was a grad student is, well, is MOND right or not? So I'll talk about that a little next lecture, but that all depended on what the third peak was. And everybody said, well, if the third peak is high equal to the second peak, MOND is out. And MOND has a very tough time explaining this. That's why what I'll say next time is my opinion, and I think not just my opinion, is the strongest evidence for non-baryonic dark matter is from the CMB. Not rotation curves, not bullet cluster, it's from the CMB. Because it's linear theory, and it's nearly impossible to get this high third peak without non-baryonic dark matter. And so this came when I was a grad student, and now to see all of this, you know, well, 2003 were the first results. It's just amazing. Anyway, and then here is the cosmic variance regime. Okay, so let me leave things at that, and then next lecture I'll tell you a little bit. This is just the TT power spectrum. We have so much more. We have TE, we have EE, polarization as well. So next class I'll tell you why the CMB is polarized, and then try and tell you what the parameters are that we get from this, and where the future is going. And now if you have questions about the dipole issue, come here after coffee break, and I can say a few words on that. Okay, great. Huh?
The K should multiply both pairs.
Oh, did I forget the K? Let me see here.
Units?
Sorry.
I was also looking at that.
Let me see here. Oh no, but I'm not sure.
They're all the same dimensions, right? Like you see that?
Oh,